Cool. Thank you so much, Judy. I greatly appreciate the invitation to kick off your webinar series. It's a pleasure to be with you today. And a few, I guess I'd call housekeeping things. Hopefully, everybody will be able to stick around to the end of the webinar when we'll have the question and answer session. I hope to be able to have about 10 or 15 minutes to field questions. If you could hold your questions until that time, that would be great. And I believe my friends at NCIT are going to help with microphone muting and other things. During the presentation itself, I'm going to turn my camera off. I invite you to do the same. And then perhaps at the end, we can all come back, turn cameras on, and have a conversation about some of the topics today. So with that, I'll get started and begin the presentation. So my topic for today is responding to transportation project challenges. New developments in geotechnical tools, processes, and workflow. I know folks that are on the webinar today probably have some interest in transportation engineering, but perhaps not geotechnical engineering. Unless you're building something like satellites, airplanes, boats, you're probably going to have a geotechnical engineer involved somewhere along the lines in your process workflow. So even if it isn't your particular area of interest or specialty, you're certainly more likely than not going to have a geotechnical engineer involved in upcoming projects throughout your career. A few disclaimers. I work for the Federal Highway Administration, and in this presentation, there are no regulations or statutes which are cited, and approaches and methods are not matters of policy or specification unless they're explicitly referenced. And the US DOT does not endorse products or manufacturers or outside entities. So if you see logos or things, they're just incidental to the presentation. A quick overview of the webinar. Geotechnical engineers play a critical role in transportation infrastructure. We're involved in what a lot of people term vernacularly as horizontal construction. A lot of what we build takes up a lot of surface area on the ground, whether it be bridges, culverts, walls, slopes, embankments, roadways. And for all these structures, geotechnical engineering is an important and vital component oftentimes to the appropriate performance, efficiency, resilience of the structures that we're building. Webinar today has two parts. One's going to be advances in characterization. I'm going to talk a little bit about new tools using multi-phase investigations. And then I'm going to turn toward what I would call a relatively new aspect of geotechnical engineering, and that's geotechnical asset management. And this includes ideas with respect to inventory, condition assessment and ratings, and part of a comprehensive look at our transportation system. So kicking off, geotechnical engineering and transportation. It's important really throughout the lifecycle process. Geotechnical engineering can occur whether or not you're in an initial project scoping phase and preliminary design, final design, maintenance and operations. Really the entire life cycle of a project can have geotechnical engineering as a component. We consider things like cost, constructability, and constraints, and are generally looking to have safe and functional structures that have good life cycle performance and cost associated with them. In my work with transportation, we've got design codes which are put out by the American Association of State Highway and Transportation Officials. And we use something called LRFD, a limit state design code, where we look at serviceability of structures, strength, and extreme events as part of the design process. What does this mean as a practical matter? Well, the statistic folks would have, you draw the curve on the left that talks about the loading and the resistances, and the idea that the loads are somewhat more well understood than the resistances. So a lot of times the bell curve for the anticipated loading is somewhat narrower. And then you have resistance. So in the diagrams in the center at the right, we generally try and make sure that the loads are less than the resistances for proper performance. The center diagram shows where you might say we have incipient failure with the idea that the loads are equal to resistances. The failure could be ductile. It's not necessarily going to be a catastrophic failure, but it would represent a degradation in performance from what we designed. And on the right, we would really like to reduce the likelihood that the loads are greater than the resistances, and we want to reduce the probability of failure or the probability of poor performance to acceptable levels. And this idea of risk and reliability or factor of safety is incorporated in our design process. How do we do it? We have to, as geotechnical engineers, go out and examine the site. This is somewhat unique. Our colleagues, a lot of times when they're doing their designs, it can be sometimes site independent. You can imagine that if you were putting in a bridge or a roundabout or designing something, it might look the same wherever you put it. That's not true for foundations. We need to take a look at what's happening with the geotechnical materials and other things like, say, the proximity to bodies of water and what's happening in the greater geological environment. So a key concept in geotechnics is that sites vary, and appropriate field investigations are really necessary to properly address site variability, risk, and reliability. We do a lot of work to measure field properties. We perform sometimes index testing, field testing, and laboratory testing. Sometimes it's direct measurements on samples, and sometimes it's indirect measurements using geophysics and involving our partners in the geology community. In the end, typically we are trying to develop engineering parameters used for design and construction. You may be familiar with some of the more common ones like friction angle, undrained shear strength or cohesion, modulus, permeability of soils, and so forth. Successful designs require appropriate data for the project, which may change depending upon the nature of the project, the quality of the data, and the amount that we have to work with. We're certainly concerned with things like accuracy, precision, and repeatability. We're also concerned with ideas that the samples are representative. And so we try and, as geotechnical engineers, choose test locations, the number of tests, and do enough work that we can have an informed design. So well-designed and well-constructed ground support and earth retention are important for a successful project. We have to look at admissible failure modes, what can happen. This is different for soil and rock and for different types of foundation or earth support systems. We have to look at the conditions at the time of construction and also take into account how something is being built. And we need to look at the long-term performance. So after it's been built, do we need to consider things like deterioration or changes that might occur in the loading conditions at some later point? Is material going to be eroded if we're in a coastal environment? Are we in an earthquake-prone region? Could there be changes in water, perhaps due to drought or flooding, or scour if we're adjacent to a waterway? So a lot of different things to consider in the design. There have been a lot of advances recently. Newer and high precision characterization tools are available. We also now have the opportunity to cost effectively do multi-phase or multi-tool investigations. And relatively recently, probably in the past 2 decades or so, with digital techniques as opposed to analog, there's been a real evolution in electronic data gathering and exchange. And with that, really, I'll call it an entire new discipline within geotechnical engineering related to geotechnical data management and use. Seismic methods are an area that have particular utility. So it may have been in previous practice, you might mobilize a drill rig, go out and take samples of the soil, and perhaps do a soil boring at each foundation element or ever so often along a proposed structure. Geophysical methods such as seismic methods allow you to do a look that is over a much wider area. And it has the benefit that it's relatively inexpensive and can provide 2D profiles such as this one. So it can help resolve stratigraphic conditions and boundary layers over larger areas. And it's particularly useful for certain types of geotechnical issues, such as seismic hazard and liquefaction susceptibility. And techniques like this also are able to record direct measurements of shear wave velocity, which are related to seismic performance. Additionally, and perhaps one of the strongest features, is if you do these investigations prior to a drilling program, you can inform that investigation. Drilling is relatively expensive and invasive, and so by using some of these methods before drilling, you might be able to save time and money. Cone penetration testing is also, I'll say, a relatively new technique in the United States, even though it has been used successfully for dozens of years. It's just not, I'll say, fully incorporated into all transportation agencies' workflows as yet. So this is a site investigation. The photo at the left is a cone penetration test rig that pulled up to a bridge washout after some flash flooding. And the diagram at the right shows a plot of some of the information that was obtained from that site investigation. They were really interested in getting the road back in operation on this particular project, and it took about an hour and a half for that rig to go from one side of the bridge to the other due to the washout, but some soundings were taken and reported back, and an engineering report was able to be issued before that truck actually got back to the office later that evening. And so the speed of the investigations is really one of the aspects of cone penetration tests that makes it particularly useful. The cone is an instrumented probe. It can provide tip stress, sleeve stress, pore water pressure. You can attach modules for seismic interpretation and resistivity, as well as a magnetometer and several other things that can be put on the probe. It provides direct engineering measurements, and so it is an exciting tool for geotechnical engineering. Something relatively new in US practice is called measurement while drilling. So sensors are attached to a standard drill rig that you might be doing your SPT or thin wall testing with to get laboratory samples. And it measures drilling performance. So it provides continuous measurements of the profile based on feedback from the drill rig's operating parameters. So you record things like the penetration rate, the rotation speed, the flow rate of the fluid pumps, the torque that's applied to the drill steel, and fluid pressures and the downthrust or the crowd that's applied. And using the feedback of these measures, you can create a plot similar to the one at the right, which actually looks a lot like a CPT plot, but it allows you to have near real-time continuous data, and you can look for changes in stratigraphy and put correlations together for material properties. And there are a number of state DOTs that are currently in the process of using this technology or purchasing drill rigs to apply it. I want to say 3 or 4 states are currently using it, and there are about 10 to 15 that are in some part of the interest or procurement process. So it's a very current, up-and-coming technology in the U.S. transportation sector. So typical site investigation for past practice. Previously, the state of practice might be drilling, finding a standard penetration test N value or the blow count. We might have taken SPT samples or thin-walled samples and done some field and laboratory testing. Today, a lot of DOTs recognize that it can be advantageous to add things to this portfolio. So now we are looking at different types of geophysics and several different methods that are involved in that, shown in red at the top. We have a number of new direct push technologies, which are relatively easy to implement now: the cone penetration test, the flat plate dilatometer test, the pressure meter. And these can measure a number of parameters, some of them near real time and consistent. So we get multiple readings perhaps every centimeter or every inch, and so increase in data density. And we also have new aspects of technologies that can be applied to rotary drilling. So I mentioned measurement well drilling, and we have optical and acoustic televiewers, and new types of laboratory testing that can be conducted on the samples. So still very important to get samples, but traditional testing can be improved and augmented by using some of these additional technologies. I talked just briefly about the idea of multi-phase or multi-tool investigations. They can be rapid and non-invasive, such as geophysics. So if it's used as a first step, it can be used to inform where to locate sites potentially for CPT or measurement while drilling, and perhaps those tests which provide relatively consistent plots of data over the depths. They can be used to target the slower and more labor-intensive standard penetration or drilling techniques. Perhaps locate sites where you might want to run a dilatometer or pressure meter test, and or recover your samples more specifically rather than a standardized program. So historically, there had always been some questions about the cost or effort involved in mobilizing twice to a site, but really, this technique is not mobilizing the same piece of equipment to a site, but different pieces of equipment so that you wouldn't need to remobilize the expensive equipment more than once, because looking at the sites in greater detail before you mobilize the expensive site allows you a better idea of what you need to do. So just a quick little doodle here of a cost example. You might say that a traditional single mobilization for 3 to 5 borings maybe takes 3 weeks and costs $30,000. So you can say, okay, I'm familiar with that. Certainly the one on the right, which has 3 different investigations, must be more expensive, right? Well, let's take a look. Geophysics normally takes less than a week, and maybe I can do several lines for $4,000. And CPT might cost a week for around $7,000. I could get 20 soundings during that time. And then maybe I only need 1 week of drilling with 1 to 2 borings for $10,000. And I can do targeted sampling. And it turns out that if I add those up, because they're different rigs, I can do them all in 1 week's time. Could be the same week if I wanted to do all 3. Or maybe consecutive weeks. And it looks like it adds up there to something around 22,000. So it's both faster and less expensive, which a lot of people find counterintuitive because it just seems like it ought to be more until you do quick calculation. So some photos here about a project example. So this was for the design for reinforcement of a 1930s suspension bridge in Idaho. It was aided by televiewer data. So the bridge shown in the photo at the left, diagram at the right shows some of the design that was necessary for looking at the rock jointing because some tieback anchors were necessary. And oops, flashback to that for a bit. But just an example of some of the other tools. The televiewers are an instrument that goes down a borehole and allows you to take a look at which direction the rock failure features and or sedimentation occurs at. And so it can be useful for the design. So that's another tool that we have in our portfolio that can be leveraged on projects. Talked a bit at the very introduction about some of the things that are happening with geotechnical data. Historically, geotechnical documents have been paper-based in terms of logs. Sometimes it's either been a physical plot of what are called fence diagrams, which are often simplified borings, plotted up historically on a sheet of paper, but sometimes and more commonly now in CAD. And then we often have physical reports, either informational data reports or recommendations for projects. Historically, geotechnical data management was largely archiving these paper lab records in geotechnical reports and boring logs, but that's changed substantially over the years. For a typical bridge project, though, a lot of times a complete geotechnical investigation might be reduced to a specified foundation type in a project plan set with information about the installation criteria and presented on a plan sheet, much like the one shown at the right here. This shows both a plan view and a profile of the location of the boring logs. Some DOTs still issue paper plan sets, some do it electronically, but this might be all that a contractor has to bid on for a project. The simplified boring logs often included material symbology and abbreviated layer descriptions, and the blow count and the N value. But for a whole project investigation, that's not really a lot of data. Oftentimes, agencies will make reports available, but they are not necessarily included in the contract documents currently. As we move toward the future, digital formats are becoming more common. Everybody has probably used Google Earth or a similar type of software program. And that plot on the left shows a plan sheet overlaid on an aerial photo. And the image on the right shows what you might have in the near future for geotechnical information in a CAD or building information management, BIM, or digital twin environment, where you have much more information about the underground space. In that diagram, some of the symbology includes cone penetration tests and standard penetration tests with the circular discs or the things that look a bit like table legs, and the foundations for the project. The shaded areas, the two sort of trapezoidal planes that are intersecting with the green and the red, are representative of an electrical resistivity geophysical survey plot. In a CAD environment, you may be able to rotate this around and take a look from different perspectives, or perhaps visualize using 3D holographic goggles or other technologies. But it's definitely a lot different than the plan sheet I showed previously. And this type of technology is rapidly coming to the geotechnical profession. Digital workflows are another aspect of current and evolving practice within geotechnics. We have an interchange standard that's currently being I'll say spearheaded and maintained by the American Society of Civil Engineers Geo Institute. It's called DIGS, Data Interchange for Geotechnical and Geoenvironmental Specialists. It's a GML, geographic markup language, and it, similar to HTML, XTML, provides a data dictionary and a schema for being able to exchange geotechnical information. So much like there are current standards for the interchange of other information, you can think of how information like MP3s for music, or the current standards for, say, HDMI digital TV. It's similar, except it's for geotechnical information to be sent through different types of digital means between software. So you could imagine that it links field information, either gained by, say, CPT or measurement while drilling directly, or from maybe a tablet where people are introducing boring information. It may come directly from lab testing devices. It may actually come from sensors that are embedded in the field, like inclinometers or piezometers for pore water pressure. And the idea is that this language would allow different parts of the workflow process to talk with one another. So analysis, data presentation, database hosting, visualization software, all part of a new ecosystem. And currently there's a provision for it. I mentioned AASHTO previously. So there's a digital interchange standard for geotechnical data. And so this has been in process for a number of years for the development, but it's starting to gain traction as BIM and digital twins come online, and with just the evolution of geotechnical digital technology generally. There is a international group for geotechnical BIM and digital twins. It's the ISSMGE Technical Committee 222. And this group is currently working on data standards with the BIM infrastructure group and working with the Open Geospatial Consortium, so a number of international groups working on the exchange of geotechnical data so that we have interoperability consistently. Currently in the international space, there are what are called development of books, where book A is related to observations and sampling. So if you want to think of that as original data, they call book B models like geological and hydrological units, geotechnical units, hazard areas, and these are generally based on interpretations and assignment of parameters rather than the physical properties. And then there's a third book, which is basically a project-based model with interpretations and projections. And currently, book C has been used for tunneling environments. And we're imagining that it will be or at least something similar to this, will begin to be used in the United States practice, again, as digital twins become more common for projects. You might ask yourself, how far away is that? Am I talking about something in the far-flung future? And the answer is no. It is something that departments of transportation are actively working on. The Utah Department of Transportation has a digital delivery group. The Iowa Department of Transportation has a strategic plan for project digital delivery. Arizona, the large image on the right is from the Texas Department of Transportation, where they are looking at letting projects digitally. And Pennsylvania DOT has a digital directive 2025. So if you just go out to your favorite search engine, type in any of these states and digital delivery, you'll find that a number of them are very interested in providing full design packages in either a CAD or a BIM environment to their consultants and contractors for the efficient bidding and production of transportation projects. So it's something that's very current. Going to swing over to the ideas of asset management for about the next 10 or 15 minutes here, and then we'll head over to questions. Asset management goes beyond design. It's an area of emerging development with respect to geotechnical performance. So traditionally, we've looked at geotechnical design as geotechnical professionals in transportation. And now we're starting to become involved in this idea of taking inventory of the structures once they've been built, looking at continuing or condition evaluation, assessment, and ratings. And why are we doing this? Well, there are new focus areas: climate change, adaptation, and resilience, integrating more with some of our partners with transportation asset management in that framework. Typically, it's been limited to bridges and roadways. Those are funded programs, but many state DOTs have expanded them either to include things like geohazards, rockfall, avalanche, or other aspects of built works that they feel that it's useful to inventory. That can be things like road signs or ADA pedestrian improvements. A lot of different things get inventoried with condition ratings today. And it's really all about spending money wisely and trying to avoid worst first for repairs, but just managing our time, money, and resources. So the benefits of transportation asset management: determine risk exposure, measure and manage safety, prioritize operations and maintenance, and incorporating data into the processes for informed decisions. So it's all about the data. And we as geotechnical engineers have a lot of data to offer in the system. We're looking to reduce delay and closure, so improving network performance. Everybody typically likes to get where they're going efficiently and safely. Reducing damage to other transportation assets. You can imagine that geotechnical assets are often soil or rock, which tend to hold up other people's stuff. So bridges, culverts, and other things are generally founded on the ground. If the ground is no longer there, that provides a problem not only for us, but for our colleagues and their structures and facilities. And then overall at the end, reducing adverse impact to travelers, commerce, and community. So what are geotechnical assets? We have a National Cooperative Highway Research Program Research Report 903 that talks about embankments over 3 meters, slopes of less than a 70-degree slope, sometimes specifically unstable slopes or ones that have been recognized to be problematic, retaining walls, roadways and subgrades, ground improvement, geohazards, and even the data itself. So a geotechnical asset can be non-physical. It might be these borings, models, and reports that I mentioned. Just a quote from the right. Should be managed, these assets, in order to realize measurable life cycle cost, risk reduction, and performance benefits for owners and users. Mentioned that assets often include geohazards. The cartoon at the left shows rock falling down the slope and potentially some erosion control and retaining walls off the right-of-way. A lot of times as transportation agencies, it's not only our own facilities that we need to be mindful of, but also adjacent and nearby either facilities, landforms, and so forth. We can think of geohazards and triggers. So landslides are a big problem, rainfall, freeze-thaw, drought, post-wildfire, mudslides and debris flows often brought on by drought or chemical changes in the soil itself. Things that our friends up in Alaska need to deal with are permafrost degradation, then of course flooding, coastal impacts, a lot of different considerations. And the interests at the bottom, sustainability, resilience, safety, project context needs to be considered, of course. So a lot of things potentially driven by extreme weather and climate change, as well as just, I'll say, typical engineering aspects of constructing on soil and rock. We're looking at life safety, damage, access and restriction to interruption. But we have technology that can help us out. So innovative materials, geosynthetics, slope reinforcement, different techniques to mitigate rock fall, and instrumentation and monitoring in some cases to find out either how well our solutions are working, or if we haven't solved the problem yet, to take a look at what's happening so we can design a better and efficient solution. Puerto Rico is a really good case example of a geotechnical group. The Puerto Rico Highway Transportation Agency has an excellent geotechnical asset management program. The upper left shows a dashboard for their culvert inventory. Lower left is a slope inventory. And then on the right is a wall inventory. They're looking at starting to do condition assessment for a number of structures, but they've started out with this asset inventory. Landslides for them are a particular challenge, especially when they come in multiple events, and in this case leave relatively large particles on the road. You can see on the photo at the left, they were lucky during the first landslide in that area, and that boulder that came down did not enter the roadway. The next event that was brought on by a later rainstorm brought down several larger boulders that basically completely closed a 2-lane highway. Alaska has, at the other end of the United States, has a very good geotechnical asset management program. These are some photos clipped from their website. They've got a geotechnical asset management dashboard with program layers, event trackers showing mapping of rockfall hazards. And they are, looking to manage their program in the face of climate change and permafrost degradation, flooding, rainfall at unusual times of the year, coastal erosion when ice that might have otherwise been present isn't there to help protect assets. So a lot of things going on in Alaska, but they have a robust geohazard analysis and condition assessment program. Other states do as well. So landslides and rockfall are not unique to Alaska and Puerto Rico. They occur throughout the U.S. and its territories. Many states are beginning to collect data related to geohazards. For those of you that are familiar with the shapes of U.S. states, this would be Ohio. They have a landslide dashboard, and obviously certain parts of the states are more prone to landslide hazards, either where there are more rivers or more topography in the mountainous areas. So it depends on things such as the geology, the hydrogeology, as well as weather and other types of events. So post-event design needs, you can imagine that if we had geotechnical projects to build a structure originally, and it's perhaps suffered some sort of event that impacted performance, getting it back into operation is important. So this is an aspect of resilience. So a frequent goal is to open the road quickly, and we often will employ some relatively fast slope stabilization techniques or soil support for ground improvement. Looking to rebuild the existing facility, a lot of times, at least to maintain and restore traffic, while a more permanent fix is designed, and often a more robust solution is put in place. So sometimes if a culvert is washed out, it may be replaced by a somewhat larger culvert. The photos here, a culvert that was through an embankment was replaced by a multi-span bridge. Sometimes moving out of the way is the least expensive option after an event occurs. This is a site where a highway alignment had a landslide that impacted 2 lanes of a 4-lane highway. So the landslide cut through the westbound lanes of US Highway 2. This landslide was actually caused by a drought. The river level was relatively low. The hydraulic pressure at the toe of the landslide was significantly reduced, and it started a landslide. And once it was moving, it was a strain softening event, and there was no way for the slope to recover. And so the area and the roadway sort of in the center middle picture dropped about 15 feet or so in the span of 2 weeks. The photo on the right shows a rebuild where the alignment was offset little more than 500 feet, and it was less expensive to buy the right-of-way and realign the highway than it would have been to try and put in a bridge or other solution. So sometimes we just need to move. Variety of geotechnical options often exist, so understanding the failure mechanisms, triggers, and geometry is important, and frequently instrumentation and monitoring are used to gain additional insight into the scale and behavior. There are exciting new developments that have been used. You can imagine that now, where we may have previously had to do airborne photographic surveys, we now have drones and unmanned aerial systems that can help us. We've got several satellite technologies, INSAR, for looking at slope movements, sometimes with significant precision. And sometimes these LiDAR flights have already been occurring. And so we might even be able to go back in time and take a look at what was happening before an event occurred for a better understanding of the site. There are a lot of benefits for asset management. I think I've touched on a few of them, but really, if we just throw the word geotechnical into some of the descriptions I showed earlier, determining the geotechnical risk exposure and decisions related to geotechnical issues and incorporating geotechnical data into the processes are helpful as one branch of transportation asset management. They really are coupled in order to do effective asset management with respect to geotechnics, the original data at the site from what it's made of, the soil and the rock and the water and its behavior is critical for an understanding of the performance of what we decide to build there. And so that data does retain its value over the life of the structure and in the event that new structures are made. So the two aspects of data and asset management definitely complement one another. And you can imagine that asset management, how well the system is performing, will inform the nature of reconstruction. So the next time there's a project, that asset management data becomes geotechnical performance data to use for future projects and or nearby projects. So a lot of value capture involved. A few concluding thoughts. As geotechnical data management evolves, so too does asset management. States are adopting geotechnical asset management components depending upon their local and regional needs. Every state is required to have an asset management program through legislation for bridges and large structures and pavement performance, but it's customizable by states for other aspects of transportation assets. So it varies a lot from state to state, and that's good. States are adopting asset management to meet their needs. Geotechnical design and construction plays a critical role in supporting our transportation infrastructure works, and appropriate field investigations are necessary to help address our site variability, risk, and reliability. And there are a host of new technologies in site characterization as we look toward geotechnical data management and challenges that we have moving forward. Today's geotechnical challenges provide a variety of opportunities. So for those of you that are students currently, certainly transportation engineering and specifically transportation geotechnics is an exciting and robust field. We have not learned everything yet. There are still things yet to know. And you have the opportunity to work in the field with geologists and professionals in newer collaborative fields such as geotechnical information, informatics, even game design and modeling for visualization, and certainly machine learning. It's a very exciting field to do a number of different things, both indoors and outdoors. We're looking toward this whole idea of the geotechnical workflow as moving toward one unified workflow design, particularly as digital design is adopted, and these digital twins can be created to model projects. And digital innovation will ultimately improve our geotechnical deliverables. I suppose in closing thought here is that geopractitioners will and do need to remember that the real world is a critical foundation for our digital architecture, and it fully remains important to visit the site and go out and determine what's really happening out where we're going to be building our facility. So bridges, culverts, walls, slopes, pavement, it's all built on soil and rock. We need to know appropriate information about that for founding our structures. And with that, I appreciate your interest this afternoon. It's time for the Q&A. So thank you for joining, and I will let's see, stop sharing the screen here and turn on my camera. And I think we're having folks either raise their hand. I see somebody with their hand up at the moment, and also if folks want to type in things with the chat, I've got some friends that are helping monitor the chat for me. So let's see. Okay, number one. Let's see who's up. Is it Jaber bin Alam? I apologize if I've
no worries. Derek, it's a great presentation. Learned a lot of things. So will the PowerPoint slides be available for all the audience, or can you make it available if possible?
I believe we are. I don't know the exact process, but I believe the presentation has both been recorded, and I can certainly provide a PDF of the slide deck.
Oh, okay, that would be great. And because I want to learn more about the digs, that's a kind of new thing I'm learning. So that's kind of interesting for me, and I will try to learn more about this and get back to you if I need any more information on this.
Yes, please do feel free to get in touch, and certainly thanks for your interest in digs. That's an exciting area of current development.
Yeah, sure. Thank you. That's all my questions.
Well, thank you. Is it Amit?
Hey, yes. Hi, Derek. Great to hear your talk. I actually have two questions on geotechnical asset management, and that's what I'm working here at Texas A&M. So is this a consensus, like the CAM is a part of TAM, like in the industry? That's I just wanted to know, is like that's how are we perceiving it as an industry, like geotechnical asset management as a part of a transportation asset management? And the next question I have is, so the states that you mentioned, Alaska, Puerto Rico, and Ohio, they've started to use geotechnical asset management. So are these based on the 903 report, or was it like done before the report came out, or they use the Excel or the macros developed as a part of 903? So just wanted to know what's being done at those two states, if you had any thoughts on that.
Yeah, with respect to the first question, because geotechnical assets are not required by law, similar to bridges and pavements, they're typically not within the formal TAM asset management framework. So right now, typically those aspects of TAM tend to stand on their own because there are reporting requirements and statutes and other things involved. When we've been developing geotechnical asset management, the idea is that it informs all of transportation asset management. So we didn't want to call it something entirely separate because it's not. And a lot of times geotechnical assets are either like physically connected or intimately adjacent to other structures and facilities. So we didn't want to say, separate it out and to say, well, this is its own discipline, its own thing. But also, too, we couldn't really connect it robustly. So it's right now sort of, I'll say, in between. It's neither fully separate nor fully integrated. We're trying to be close friends with TAM is what it amounts to.
Right.
And I think we can be successful in that model. And I believe that's the case with other things as well. Like anything that isn't like has reporting requirements or is required to do, it's always going to be a bit separate but equal. But we'll see how that plays out. It'll be interesting as time progresses. With respect to the second question, many states have asset management programs. Ohio has one that they use particularly for their, I think their retaining walls and also for underground mining that went on in the state. So they're trying to keep a handle on the risks associated with mines that go under their highways. Washington State and Colorado have well-developed programs for looking at their geohazards for rockfall management. I couldn't say specifically I know of any state that has used the 903 software. Puerto Rico may have, but because their program, I think, or at least some of them may have been adopted around the time that came out, but it may have also predated it. But certainly states that are first starting to do it, if it's not modeled directly on it, it's very similar to some of the things that are in that report. So if you have a state agency that has yet to start, it's an exceptional grounds or resource to begin a program.
Great, thank you.
Sure. Claudia. I'm not sure if you're on mute. I can't hear you. Let's see. Yeah, if you're not on mute, maybe it's an issue with your microphone or something.
Hey, Derek, I have a question in the chat. Can measurement while drilling systems be retrofitted onto older drill rigs, or do you need a new drill rig?
MWD systems can most definitely be retrofitted. So a number of providers are now starting to offer it, where you can buy a package and say, hey, I want a new drill rig. I'd like to buy it with MWD, and it'll come included then with the sensors and the data acquisition system and other things with it. The state agencies that have been doing it, I believe, have all done basically aftermarket additions to it. So if you have a drill rig, it is, I'll say, relatively easy to add on the equipment. You have to install things like the torque and the fluid flow sensors and other things onto the rig and put them in places that where they aren't going to be subject to damage from the various mechanics of setting up and operating the rigs. But it's quite common to do a retrofit. And I want to say the prices we've been seeing, I believe, for doing that are somewhere between like $25,000 and $40,000. I believe that's correct.
Can you hear me now?
Yes.
All right. Well, thank you very much for your patience. Well, you talk about climate change adaptation, and this is all great, and actually, this is the way we should all be going. But one of the things that I'm always wondering is the seasonal changes in climate and how we as DOTs are embracing that this is actually one of the main problems we have, and we just allow it to happen without, just by repairing and maintenance instead of trying to figure out how to design for that. In the last CNPC's report on moisture measurements, 55% of the DOTs reported that they have moisture sensitive soils. So that, those susceptible, expansive soils, we know all of these. However, we had 90% of these DOTs that they don't even have a specific monitoring program for highly sensitive soils, for example. Or they do have 68% do not conduct even long-term moisture measurements, or 70% do not conduct any remote sensing. And the worst thing, we were talking about all the data collection and how important it is, 85% of the DOTs do not maintain their own moisture database, pressure database for the soil. So how we can just focus also on seasonal variation that actually those are the ones that are damaging all of the roads. And it seems like we are not getting to that point with the DOTs are doing the work to monitor this order.
Yeah, my colleagues in pavement especially, will comment on the vital importance of understanding moisture. Not that it isn't equally or also important for, deep foundations and other structures. I think a lot of times there's I'll say a perception of permanence when people do site investigations, that they'll, when you go out and investigate the site, they'll just sort of assume that things are going to be like they were when they investigated it. So it's even, I'll say, a relatively recent advance when people are looking at seasonal moisture and groundwater levels. For certainly like the larger mega projects and design build, today you'll see people putting in piezometers and looking at the changes between summer, winter, spring, seasonal variation and pool levels. It wasn't that long ago, or even that was uncommon. But I think certainly when you have shrink swell soils, it's important for pavement design. So definitely an area of research that needs to be brought to more attention.
Very good to see you. It was a good presentation. This is Athar Khan from Indiana.
Hey, Athar.
Hey. Yeah, we have an asset management program in Indiana, and I think we're doing for like 5-6 years now. Basically involve retaining structures, landslides, special feature type project. And now we are working on developing some other aspect of the geotech asset. My question boiled down to is most of the geotech beside the above ground structure is, I mean, you can have inventory like foundation, whether it's bed footing or deep foundation, but how you gonna assess the conditions and the criteria you're gonna develop without, unless you have a problem, then it's gonna show up on the surface. But the underground foundation, how you expect to assess that?
Yeah, that's an excellent question. When most everything else that we have, we can inspect by either direct observation or I'll say relatively inexpensive sensors. So you can imagine that if I'm trying to determine how my building is performing, that I might have sensors in the heating, ventilation, and air conditioning system, or power consumption, or something in wastewater. Normally you can determine how something is working either by looking at it or by poking at it in some way, and that's often done with sensors. So potentially we could include some smart piling, maybe not every pile, but you might have some sensors that are able to determine if there are changes in either the strength or the stiffness, or some things to measure corrosion or deformation if something moves oddly, particularly for retaining structures. There could be ways to do it, but certainly moving from condition inventory to condition assessment is an area that needs a lot of work in moving forward to determine efficient ways to do it. I think remote sensing has a lot of promise for the potential for determining things based on deflection, at least as far as retaining walls and other hardscapes. And I think there are some technologies that we might be able to introduce with acoustic and ultrasonic sensing for things like piles and drilled shafts. Exciting opportunities.